Okay, good morning, everyone. Hello, it's Monday morning. And okay, just for your information, we considered the product rule and quotient rule the other day. And please remember that if we have a product of two functions, say f of x times gx, then when this function is differentiated, we need to differentiate one by one, meaning you first differentiate the f function, then you multiply gx without differentiation, and then you add f of x multiplied by the derivative of the next function, which is g prime of x. So that was the product rule. So that was the derivative when the product of two functions is given. Now, in case of the quotient rule, we have the quotient of two functions. So, for example, f of x over gx. Then what did I tell you about the derivative of this quotient? You first differentiate the numerator. Okay, so the derivative of the numerator multiplied by denominator minus, okay, we have a minus sign here, and then you multiply the numerator times the derivative of the denominator. And this whole thing is divided by the square of the denominator. So the quotient rule is a little bit complicated to remember, but somehow you need to memorize it. Okay? Or at least you need to write down this formula on your cheat sheet so that you can use it when such a function is differentiated. So we considered one example here in the example. So the numerator is x squared plus x minus 2, and the denominator is x cubed plus 6. So you first differentiate the numerator. So x squared plus x minus 2 is differentiated, multiplied by the denominator without differentiation. And then you minus, okay, the numerator, which is x squared plus x minus 2, multiplied by the denominator, the derivative of the denominator. So given this x cubed plus 6, you differentiate it and then multiply that with the numerator. And this whole thing is divided by the denominator, x cubed plus 6 squared. So that is the y prime, the derivative of this function. So please remember this. Okay. So let me give one example. So please be careful. So if I have, say, x squared plus 1 multiplied by, say, x minus 3. In that case, when this whole product is differentiated, you need to differentiate one by one, meaning you first differentiate the first function. You differentiate this multiplied by the remaining x minus 3 without differentiation. And then you add, in case of the product rule, you need to add the next term. Next term is the first term unchanged, and then you differentiate the second term. So if I differentiate the x squared plus 1, okay, then you first differentiate x squared and then you differentiate 1. When you differentiate x squared, you get 2x. When you differentiate 1, you get 0. So the derivative of x squared plus 1 is 2x. So this 2x is multiplied by x minus 3. And then the next term is x squared plus 1 without differentiation. And then you differentiate the second term. So if you differentiate x, you get 1. If you differentiate negative 3, you get 0. So the derivative of x minus 3 is just 1. So if I expand the first term, you get 2x squared minus 6x. If I expand the second term, you get x squared plus 1. So when I combine 2x squared with x squared, you get 3x squared. And then you have negative 6x. And then you have a 1. So this 3x squared minus 6x plus 1 will be the derivative of this product. Okay. So if I have a product of two functions, you need to differentiate one by one. Okay. Note, never, okay, compute the derivative of x squared plus 1 multiplied by the derivative of x minus 3, which is totally wrong result. Okay, so this is not what you want. When you have a product of two functions, you need to differentiate one by one without altering, without differentiating the other terms. So please be careful. Let me consider another example. So suppose that I have, say, e to the x times x squared minus 1 times, say, x plus 1, or x squared plus 1. So if I have a product of three functions, then the formula is the same. You need to differentiate each function one by one without differentiating the others. So when I differentiate this whole product, you first differentiate the first function, okay, multiplied by the other function unchanged. So you put x squared minus 1 times x squared plus 1 unchanged. And then what is the next term? X squared minus 1. So you do not touch e to the x or x squared plus 1. You just differentiate the 1 in the middle. So if you differentiate x squared minus 1, you multiply that derivative with the other function. And then we have one more term, x squared plus 1. So you do not touch the other two terms, but if you need to differentiate the third one. So if you remember that when you differentiate e to the x, you get e to the x. So you have e to the x. That's the derivative of the e to the x. So you multiply x squared minus 1 times x squared plus 1. And then when I differentiate x squared minus 1, when you differentiate x squared, you get 2x. When you differentiate negative 1, you have just 0. So you multiply e to the x with 2x times x squared plus 1. And then you do not touch these two terms, and then you consider the derivative of the third one. So when you differentiate x squared, you have 2x. When you differentiate plus 1, you get 0. So, okay, so when you have three terms, you first differentiate the first one without touching the others, and then you differentiate the second term without touching the others, and then you differentiate the third one without differentiating the other terms. Okay, so that's how you consider the differentiation of the product of some functions. So in this result, e to the x is common. So I have e to the x, and when I consider the expansion of x squared minus 1 times x squared plus 1, you get x to the fourth minus 1. You can check. And then from the second term, 2 and 2x is multiplied by x squared, you get 2x cubed. And then 2x plus 1 will give you 2x. And then when x squared minus 1 is multiplied by 2x, you get 2x cubed minus 2x. So e to the x times x to the fourth, and 2x cubed plus 2x cubed will give you 4x cubed. Now plus 2x and negative 2x will be erased, it will cancel out, and we have one more term, negative 1. So that will be the derivative of this product. So when you have a product of several functions, you need to differentiate one function at a time while you do not touch the other terms. So that's what happens. If I have the quotient of two functions, we have slight different formula, right? So if I have e to the x, say, over x squared minus 1, when you differentiate this quotient, okay, what is the formula? You first differentiate the numerator, which is e to the x. So you differentiate e to the x multiplied by the denominator, which is x squared minus 1. And then you need to subtract the next term. Okay? And then what is the next term? You multiply the numerator, unchange it, and then you multiply the derivative of the denominator. So x squared minus 1 is differentiated, and then it is multiplied by e to the x, the numerator. And then what is the denominator in this case? Denominator is the original denominator squared. So when I differentiate e to the x in the numerator, you get e to the x multiplied by x squared minus 1 minus e to the x times the derivative of x squared minus 1. If you differentiate x squared, you get 2x. If you differentiate negative 1, you get 0. And then we have x squared minus 1 squared. So in the numerator, e to the x is common. So we have x squared from the first term, x squared minus 1 from the first term. And then from the second term, we have negative 2x divided by x squared minus 1 squared. So that is the derivative of this quotient. Okay. So here is the summary of what we have derived. So if I differentiate a constant function in x, you get 0, constant 0. If you differentiate x to the n, you get n times x to the n minus 1. If you differentiate e to the x, you get e to the x. In case of constant multiplication or addition of two functions or subtraction, you can perform any of these before the differentiation or after the differentiation. But in case of the product and quotient of two functions, you need to be careful. Please be careful about this. So sorry. Okay, so please careful with this, the product rule and the quotient rule. So before we go to the next section, let us consider one more example. Okay, so suppose that I have f of x which is defined by, say, e to the x times x minus 1. Okay. Now, find the tangent line when x is 1. Okay, x is 0 for simplicity. So in order to find tangent line, we need to find the slope of the line. And then, so we first require the slope of the line. So in order to find the slope of the line, we need to differentiate the given function and evaluate the derivative at 0, right? So that will give you the slope of the tangent line. So if I differentiate this uppercase f, then actually it is the product of two functions. So if I differentiate this, then you need to differentiate each function one by one. So if I need to differentiate e to the x first, without differentiating x minus 1, and then plus e to the x times the derivative of x minus 1. So if I differentiate e to the x in the first term, you get e to the x multiplied by x minus 1 plus e to the x times the derivative of x minus 1. When you differentiate x, you get 1. If you differentiate negative 1, you get 0. So e to the x is common. So if I combine these two terms, we have x minus 1 plus 1. So that will give you x times e to the x. And I want to find the slope of the tangent line when x is 0. So if I evaluate this f prime at 0, so if I plug in 0 to this result, you get 0 times e to the 0. E to the 0 is 1, but 0 is multiplied. So the final result is 0. Okay, so the slope is 0. That means the tangent line will be horizontal. And what else do I need? We need the y-intercept. We need y-intercept or one point arbitrary point on the curve. So to find this point on the curve, I want to evaluate this function at 0. Okay. So if I evaluate my function at 0, then e to the 0 times 0 minus 1. E to the 0 is 1, and 0 minus 1 is a negative 1. So the value is negative 1. So that means 1 point on the curve is this. So this curve passes through 0 and negative 1 point. So if I combine these results, then what is the tangent line? We are looking for a horizontal line. So what we need is just one y value, right? So the tangent line will be y equals negative 1. This is the tangent line, okay, to the curve when x is 0. So I may ask such a question, right? Or what if I consider the following question? So if I give you a gx function, which is defined by, say, x squared plus 1 over e to the x. And then if I ask you to find the rate of change, instantaneous rate of change of this function when x is 0. So if I consider this instantaneous rate of change of gx function at 0, if I ask you such a question, then I'm asking you to differentiate the given function, right? So I need to evaluate the derivative of the function. And I have the quotient of two functions. So what is the quotient formula? You first differentiate the numerator multiplied by denominator, and then you subtract the numerator without differentiation multiplied by the derivative of the denominator, and this whole thing is divided by the denominator squared. So if I differentiate x squared, you get 2x. If I differentiate plus 1, you get 0. So the derivative of x squared plus 1 is a 2x. That is multiplied by e to the x minus x squared plus 1 times the derivative of e to the x, which is e to the x. And then e to the x squared is in the denominator. So in the numerator, we have e to the x. So if I write down e to the x as a common term, then the remaining terms are 2x minus x squared minus 1. And then I have e to the x squared in the denominator. So after cancellation of one copy of e to the x, you have negative x squared plus 2x minus 1 in the numerator, and then I have e to the x. So if I evaluate this g prime at 0, we get negative 0 plus 2 times 0 minus 1 over e to the 0. E to the 0 is 1, so the final value will be negative 1. And please remember, note that I have this negative 1 because I had negative sign in front of x squared plus 1. So the instantaneous rate of change of this gx function at 0 will be negative 1. So you need to remember the meanings of this derivative. So we could consider some mathematical formula to derive the derivative of a function, and that implies the slope of the tangent line, or sometimes it may represent the instantaneous rate of change of the function at certain point. So that's what we had the other day, the product rule and quotient rule. Now I'm going to expose new formula today, which are very important, very important. So let us consider this new section. Okay, the derivatives of trigonometric functions. Now in the past, when I considered this derivation of the derivatives of sine or cosine, I proved some formula, some basic formula. Okay, but I don't want to prove those simple things today. I will just introduce some final results regarding the derivatives of trigonometric functions because some basic formula could be proved with some theorem later. Okay, so anyway, let us consider the differentiation of trigonometric functions like sine x. So I want to consider the differentiation of sine function. And first I want to use I want to follow okay, you can read this section. So I want to use what is the definition of the derivative of a function. So in order to find f prime when f of x is sine x, I want to use the definition. So what is the definition of the derivative? You first consider the average change of the function from x to x plus h, and then you let the step size h go to 0. So we need to consider the difference between sine x plus h and sine x, and then you divide that difference by h, and then you decrease this step size h. Now, in case of this sine x plus h, we learned some formula that can be expanded to sine x times cosine h plus cosine x times sine h. So we have this three terms in the numerator and h in the denominator. So let me consider only two terms, sine x cosine h minus sine x. And then let me consider the other term, the next one, cosine x sine times sine h over h. And then I will let h go to 0. Okay, please note that I am decreasing the value of h, not x. Okay, so we are considering the limit in h. So in terms of h, x is not an important, and x is not a variable. That means sine x or cosine x are just values, some numbers. In this expression, h decreased to 0, not x. X is fixed. Okay? So x is fixed, while the value of h decreased to 0. So please remember this. So sine x is just it is a constant in terms of h. So, okay, right? So limit of two functions can be written as limit of sine x times cosine h minus 1 over h plus limit of cosine x multiplied by sine h over h, right? So the limit of the sum of two functions can be computed as the sum of two limit values. Now in the first term, I have the product of two functions. So the first term can be split, right, as the product of two limits in h. And in the second term, we can also split this as a product of two limits in h. So as I said, I'm decreasing the value of h, but x is a constant value. So when h decreases to 0, the value of sine x or the value of cosine x are not changed, right? So as h goes to 0, the limit of sine x will be still sine x. And limit of cosine x will be still cosine x. Okay? So This first term is sine x. We just consider this first term of the first, right? And then we consider this first limit in the second term. So what remains will be the limit of cosine h minus 1 over h and limit of sine h over h. And regarding these two, so in the past, I proved these two limits. I consider it, I, I derived these two limits formally. But today, I don't want to do that. Instead, I want to introduce one, okay, actually two formula. The limit of sine h over h as h goes to 0 will be always 1. Okay, please remember this. This is always 1. And limit of cosine h minus 1 over h will be 0. Please remember this, especially if you came from engineering departments. This is a very important formula in engineering departments. I mean, this formula is used in many fields of science. Yes, even economics use this. But if you came from engineering department, it is a must. I mean, you need to remember, you need to memorize, you must memorize this formula. Okay, so the limit of sine h over h will be not 0, not infinity, but 1. Okay, so that is a very important formula. I mean, okay, and later if you came from engineering departments and you will define the sinc function, right, based on this fact. So we are not going to consider that one though, but this limit of sine h over h will be 1 as h goes to 0. And limit of cosine h minus 1 over h will be 0. And I will postpone the proof of these two. Okay. So if I plug in these results, then the limit of the sine x will be sine x, but that is multiplied by 0. And limit of cosine x is cosine x, and that is multiplied by 1. So the first limit will be 0, and the second term is just the cosine x. So, so we have a very important formula. The derivative of sine function will be cosine x. You need to remember this. So as an example, if I consider the product of x squared times the sine x, we have a product of two functions. So as I said, you need to differentiate one by one. You first differentiate x squared multiplied by the remaining, in this case, sine x, plus you do not touch the first one, but you differentiate the second term. So when x squared is differentiated, you get 2x, and that is multiplied by sine x. And then x squared is unchanged, and sine x is differentiated. When sine x is differentiated, you get cosine x. So that is the final result of the differentiation. So please remember this. And if you apply the similar idea to the cosine function, you can prove that the derivative of cosine will be negative sine x. Please remember, we have this negative sign in front of sine function. And in case of the tangent is defined by the quotient of sine over cosine. So I can use the quotient rule. So what is the quotient rule? You first differentiate the numerator multiplied by the denominator minus the numerator without differentiation multiplied by the derivative of the denominator. And then you divide the whole stuff by the square of the denominator. Then when sine x is differentiated, you get cosine x multiplied by one more cosine x minus sine x times the derivative of cosine, which is negative sine, over cosine x squared. So we have cosine x squared, and since we have two minus a sign in front of sine, we get plus sine x squared over cosine x squared. So sine squared plus cosine squared will give you the value 1, and we have cosine x squared. So 1 over cosine is a secant function. So we have secant squared, and that is the derivative of the tangent function. Okay, so we have this secant function squared. So by combining the quotient rule, we could derive these 6 formula for the derivatives of these trigonometric functions, the sine, cosine, tangent, okay? And please remember, when you differentiate trigonometric functions which start with c, you have negative sign. Okay, so if you look at this, then it might be easier to remember. For the other 3 functions, sine, tangent, and secant, when they are differentiated, the sign is still plus. But when you differentiate cosine, cosecant, cotangent, you need to put negative sign in front of certain functions. Okay, so you need to memorize them, or at least you need to write down in the formula. But if you came from engineering, and since many of you came from engineering departments, you need to memorize at least 4 of them, the derivatives of sine, cosine, tangent, and secant. Okay, so you need to memorize these 4 formula at least. Or at least you need to memorize these 2, and then you need to derive the other 4 using the quotient formula, quotient rule. Okay, that is fine. I mean, in high school days, I just remembered, I memorized the derivatives of sine, cosine, and tangent only, because memorizing 6 formula was a little bit difficult. But okay, so it's up to you. You can, and then if needed, I just apply the quotient formula to derive the derivatives of secant or cosecant or cotangent functions. Okay, so it's up to you. You can memorize them, or you can write down those formula on your cheat sheet. Okay, anything is fine. But if you came from engineering, probably you need to memorize at least to 4, the derivatives of sine, cosine, tangent, and secant, for your convenience, I guess. Okay, so we just considered this example, and well, if you look, suppose that I have some function f of t defined by 4 cosine t. And I have lengthy statement describing some situation which occurs in physics or engineering. And since I am a math professor, I'm not interested in, I am interested, but I want to consider only in this example the derivative or second derivative of this function f with respect to t. So given this f of t, what will be f prime? If I differentiate f prime, well, 4 is multiplied, but I can multiply this 4 after I differentiate cosine t, right? So you can multiply 4 to the derivative of cosine t. If I differentiate cosine, you get negative sine. So the derivative is negative 4 sine t. Okay, if I'm interested in the second derivative as well, you can consider the differentiation of negative 4 sine t. And as I did above, you can multiply negative 4 once I complete the differentiation of the sine function. So if I differentiate sine function, the formula was the cosine t. So if I multiply negative 4 to this, you get the second derivative. Okay. Well, you can continue and you can find a third or fourth derivative if needed. But anyway, I can find some derivatives. Now, if you look at the textbook or my lecture note, some examples have some problem like this. So that the textbook guides okay, where such problem occurs in real world situation. Okay, so that might be helpful in some cases, but we are going to consider only the mathematical aspect. So probably in the exam, I will give you the function f, and then there are three possibilities for the question. Okay, so the problem type in our exam will be one of the three cases. One, given f of given f of t, say, or f of x, okay? Type 1, I will ask you to find, say, y prime or f prime of t directly. Or I will find the tangent line at some point p, or I may give you only x value. Because if I give you x value, then the coordinate of this point p will be 1 and f of 1. So you can find the coordinate of this p when only x value is given. Or I may ask you to find the instantaneous rate of change of this function f when when t when x is, say, 0, something like this. So Only okay, these will be asked in the exams. Okay, but if you go back to your own departments, okay, then you should be familiar with these real world cases occurring in your departments. But for simplicity, in our class, okay, we will focus on only mathematical aspect. And I will ask in one of the three types. And yeah, so you don't have to worry about some expression like velocity or acceleration when certain displacement function is given. Okay, we are not going to consider that type of expression in our class. We will just to focus on just the calculus and mathematical terminologies. Okay, and as I said, in the past, I proved this formula. The limit of sine theta over theta as theta goes to 0, and the result is 1, not 0, but 1. And limit of cosine theta minus 1 over theta will be 0. Now, we will check these results later. Okay. As I said, I'm just postponing the proving this formula. I will consider the proof of these two. Okay, but I'm not going to do that today. That does not mean these two are not important. They are very important formula. Very important. So you need to memorize this, especially number formula 5 is very important. The limit of sine theta over theta is 1, not 0, not minus 1, or not infinity, but 1. This is a very important, okay, result. Good. What does that mean? The limit of sine theta over theta is 1. That means when theta is small enough, sine theta and theta will be very close in value. Okay? Or in other words, as the theta decreases 0, sine theta decreases 0 at the same speed. So sine theta and theta decrease to 0, right? Sine 0 is 0, and right? So as the theta goes to 0, theta and sine theta, both functions decrease, right? And they decrease at the same rate. So that's the meaning of this expression. But anyway, you don't have to memorize the meaning of this, but you need to remember this result. The limit of sine theta over theta as the theta goes to 0 is 1. I'm just considering the limit as the theta goes to 0. Okay? I'm not talking about the limit as the theta goes to infinity or pi or not other value but 0. So let us consider the following limit. So suppose that we have this function sine 7x over 4x, and then I want to find the limit of x goes to 0. Then then I can just rewrite this sine x 7x over 4x like this. Sine 7x over 4x can be written as 47 times sine 7x over 7x, right? And so this is limit of 7/4 times sine 7x over 7x as the x goes to 0. Now, we know that certain constant like 7/4 can be multiplied after the limit is considered. So I can multiply 7/4 once I consider this a limit of sine 7x over 7x as x goes to 0. Now, as x goes to 0, 7x will also go to 0, right? So, as so as 7x goes to 0, I'm looking for the limit of sine 7x over 7x. And the formula says the limit is 1. So this limit will be 1. And that 1 is multiplied by 7/4. So 7/4 will be the final limit. Okay. One more example. So if I have sine, say 2x over square root of 2x as x goes to 0. So let us consider the case when I have just the square root of x. Okay, in that case, the formula says the limit of sine h over h as h goes to 0 will be 1. That is the formula. So in the given problem, I have sine 2x. So this 2x will correspond to h. In other words, you want to define h by 2x. Then x will be h over 2. So square root of x will be square root of h over 2. That is square root of h over square root of 2. And as x goes to 0, 2x, which is h, will go to 0. So if I rewrite this expression in terms of h, we have limit of something as h goes to 0, and I have sine h, but denominator is not h. We have square root of h over 2. So to have just the h, I need to, okay, first of all, let me just handle this 2 in the denominator of the denominator. So that is 2, okay, because that is limit of this h is 1 over 2 times, oops, so I have 1 over 2 times sine h over square root of h as h goes to 0. So I have 2 in front of the limit function, and then I have sine h over square root of h. I do not know this result. What I know is that the limit of sine h over h will go to 1. So to make h in the denominator, let me multiply square root of h in the denominator. Then I need one more square root of h in the numerator to get the equality, then what I have is 2 times of limit of this portion will give you sine h over h as h goes to 0. And then we have the multiplication by the square root of h. So limit of this product is the same as limit of the product of the limit function. So this limit multiplied by the limit of square root of h as h goes to 0. The first expression is conversion to 1. The second limit will go to 0. So the product of 2 and 1 and 0 will be 0 in this case. Okay. So in this example, we have some expression that is similar to the previous example, but this square root of x in the denominator changes the result. So in my previous example, when I have the limit of sine 7x over 4x, okay, you need to have some common expression in the sine function and the denominator, and then that common term must decrease to 0. Okay? So in that case, we get this formula. And if I have limit of sine 2x over square root of x, we have slightly different result. Now, one more example. So in my previous example, in case of sine 7x over 4x, and then if I consider limit of, say, x goes to pi, not 0, then how can I find the limit? Sine 7x is a continuous function. 4x is continuous. And this continuous 4x function in the denominator is not 0 when x is pi. So note that both sine 7x and 4x are continuous, and that this 4x is not 0 at x is pi. So in that case, sine 7x over, so that means, so this sine 7x over 4x is continuous at this value, pi. So I have a continuous function, and you are looking for the limit as x goes to pi. So what you can do is you can evaluate, okay, that function at pi. So you can just plug in pi sine 7 pi over 4 pi. 4 pi in the denominator is not 0, but sine has the value 0 at 7 pi. So the value will be 0, not 1, not 7/4, okay? So the previous formula is applicable only when you consider limit of something, okay, sine h over h as h goes to 0. So the previous formula considers the limit as h approaches 0, not other value. And so in this case, limit of x, limit of some this expression as x goes to pi, then you just use the fact that the given function is continuous. So when you apply a mathematical formula, you need to check whether some conditions considered in that formula are all satisfied. So, as I said, sine h over h. So, h inside the sine function and h in the denominator are the same. Okay? And then you consider the limit as h goes to 0. So, in this example, I have sine 2x. So 2x is the argument of the sine function. In the denominator, we have the square root of x, not 2x. So I need to multiply certain function to get the same argument. And then that may change the final result. So please be careful when you apply that formula. Okay? Now, this chain rule is one of the most important formula in our class. Okay, this chain rule has many names. Okay, so if you take some advanced math class, they sometimes say Radon-Nikodym theorem, change of measure, or some other names. Okay. Oh, I'm sorry, not Radon-Nikodym theorem. Sorry about that. I got confused with the name. So not Radon-Nikodym, not change of measure. Okay, this is slightly different. The chain rule, but that is related though. Okay. But anyway, the let me skip the explaining parts as well for the class because I mean for this slide you can just read the slides, and the slide also does not prove the formula, but they just mention the final result. The claim of the chain rule is, even though we are not going to prove, is that if you have the composite of two functions, so I have the composite function, not product. Right? So if I have the composite of two functions, then when that composite function is differentiated at x, this is what you get. So you first differentiate the derivative of the outer function evaluated at the inner function multiplied, so this is the multiplication, multiplied by, that is the derivative of the inner function. Okay. So that is the chain rule. You need to, for this one, please memorize this result because that is used quite common, quite, okay? So we frequently use this chain rule in our class. So please try to memorize the formula. So if I have the composite of two functions, then you first differentiate the outer function and evaluate that outer function at the inner function, and then you multiply the derivative of the inner function. So I have this formula, example. So suppose that uppercase f is defined by the square root of x squared plus 1. Then that is the composite of two functions f and g. Okay, we first derive x squared plus 1, and then we apply the square root function. So the outer function is the square root function, and the inner function is x squared plus 1. So f of u is the outer function, and g of x is the inner function. So what you need to do is you first differentiate the outer function. F prime is considered. Since so square root of u is considered, the derivative is 1/2 times u to the negative 1/2. In other words, you get this one. And if you differentiate gx, you get 2x. So as I said, you multiply the derivative of the outer function evaluated at the inner function. The inner function is x squared plus 1. So you plug in x squared plus 1 in place of u. So you get 1 over 2 times square root of x squared plus 1. So this is the derivative of the outer function. The derivative of outer function evaluated at the inner function. You multiply that result by the derivative of the inner function. So you get this result. Okay. And you can read this. Oops. Okay. So before we go to the next part, let me consider some example. So suppose that f of x is given by, say, sine x to the x squared, to say 2x. Oops, not 2x. Sorry about that. Say 2. Just, okay. Then there is the composite. This is the composite of f of u, which is just a square function, and g of x, which is sine x. So this sine x is evaluated first, and then that sine x is given to the squared function. So the outer function, this is your outer function, and this is your inner function. So if you want to find the derivative of this f, the uppercase f, you first differentiate the outer function. Then what is the outer derivative of the outer function? If you differentiate u squared, you get 2 times of u. Okay, and that u is replaced by the inner function, which is sine function. So that is the derivative of the outer function evaluated at the inner function. You you shouldn't forget the derivative of the inner function. You need to multiply the derivative of the sine function. What is that? That was cosine function. So you get 2 sine x cosine x. So that is the derivative of this composite. Okay. Another example, if I have, say, gx defined by e to the cosine x, then that is the composite of the exponential function and the cosine function. So the exponential function is the outer function and cosine function is the inner function, as you can easily check. So the derivative of this g of x will be the derivative of the outer function. What is the derivative of the outer function? What is the derivative of the exponential function? Exponential function evaluated at the inner function. So that is the derivative of the outer function evaluated at the inner function cosine. And then you need to multiply, okay, what? The derivative of inner function. What is the inner function? Cosine. And what is the derivative of the cosine? Negative sine. So the final result will be negative sine x times e to the cosine x. So that is the derivative of this g function. So when you have the composite, which is very common, okay, you need to apply the chain rule. So you need to apply this chain rule quite often in many fields, especially in our class. We always consider the chain rule. So you need to memorize this formula. Okay, and this is very important. Okay, then what else do we have? Yeah, yeah. Okay, so let me consider this formula after the break. Okay, so let's take a break for 15 minutes. Okay, and then let us resume. Okay, at 10:30. Okay, okay, then see you. Okay, take a break. Let's take a break.